So we start with oscillators quickly today. Last time I was talking of an oscillations and I gave an criteria which is called Barkhausen criteria, which says the loop gain should have a value equal to 1, either it should have a magnitude equal to 1 and phase accordingly, or phase imaginary quantity may be 0 and only real Tj omega may be only real values. Okay. If that occurs, we say that oscillations will start or sustained. The first of that version I said that you have a phase shift oscillator. Basically we want 180-degree phase shift from the network, feedback network, and we need 180 will come from the transistor. So this is the first of the series of oscillators which we use. This is for discrete transistor. This RSCS is of course a bias network, so just forget about it. This is the load, and I have 3 RC ladder network kept here, and the output of the final RCR is fed back to the gate of the transistor. So obviously you can see the voltage drop across this R, which is nothing but this is, remember, this is my V0, okay, and this is my VF. The whatever is voltage here is returned to this. Now the criteria for oscillation should be that this RC, CR should give you 60-degree phase shift. Is that correct? So 3 of them will give how much? 180-degree phase shift. 180 will come from transistor. So total feedback will be 360-degree in phase. Is that correct? In phase. So if the return is in phase, oscillation builds, and that's what the circuit is about. Please remember, drop across this R is VF. So this is the equivalent circuit, GM VGS. VGS is the gate, and right now assume, which is very fair in case of MOSFET, that the input impedance of MOSFET is infinite. Okay, though it is not really infinite, but it is good enough for infinite. R0 is the output resistance, RD is the load which I kept, and I call it R. This is given as Cedar Smith, so nothing great about. R0 parallel RD is I call RD dash, and then this is a phase shift network. How do I adjust 60-degree for any CR network? The impedance of a CR is how much? 1 upon CS plus R. The tan inverse imaginary by real value is the phase. So adjust your RC value such that it gives you a phase of 60 degree. Is that okay? The point, just simple RC, and you find that it will give you a phase of imaginary tan inverse or imaginary by real, and if I put RC correctly, I can get at a frequency of oscillation, this value should be equal to 60 degree, and if that 60 is attained, 180 will be this. So I put an equivalent circuit of this, which is very simple, nothing great, we have done n times, okay. So you don't need me to say how it is done. And I solve this without, I will not show you all of it. I use Kirchhoff law, I1 current in this loop, I2 in this, I3 in this, wrote 3 equations for 3 loops, okay. For this, I1 times RD dash plus 1 upon CS minus I2R is GM RD dash VGS with a minus sign. This is first for this loop, then for the second loop this equation, then for the third loop this equation. Is that okay? Simple Kirchhoff law, nothing very serious. This is a KVL going to be done. At every loop currents are assumed. We write 3 equations. Please remember, I1 flows in this, but I2 flows in this opposite direction. That's why the signs. Okay, this you are done in your basic circuit courses, so there is nothing great about. As I say, there is no RA, there is no source resistance there. Is that okay? So if I write these 3 equations, and you need not, because this is given in Cedar Smith, you can always, and this is a trivial network. At the end of the course, if you cannot solve this network, we will have a problem of the course itself, okay. Then the feedback voltage, as I already said, the drop across the final R, you can see from this circuit, sorry. The current in this I3R is essentially the feedback I3R essentially is the feedback voltage. So it is I3R is Vf. We also know the loop gain. This is a feedback circuit. So loop gain is AOL times beta, which can be written as V0 by VGS into Vf by V0, or essentially it is Vf by VGS. I substituted all that equations, 4 equations which I used, four equations I gave you. Find values corresponding to all this and you get this expression which can write now. The loop gain Ts, loop gain is also called return ratio, okay, some books. So it is Vf by Vgs, which is minus Gm Rd dash upon phi 1 minus something plus j time 1 upon omega Rc cube minus 6 times 1 upon omega Rc, and I substitute S is equal to j omega, okay. I have substituted S is equal to j omega. Now what is the Barkhausen criteria? We said that the real value being 1, it satisfies all of it, okay. So what does mean if the real value has to be 1, the imaginary quantity must be 0, is that correct? The real part is magnitude wise 1, so the other part must be 0, and if that occurs, the condition of under that condition to oscillate 1 upon this term should be 0, which gives me a value of omega 0 as 1 upon root 6 Rc. So can I now fix my frequency? By proper choice of Rc, I have my oscillating frequency which is 1 upon root 6, 1 into Rc. Now if I take the magnitude, which has to be how much? 1. So I use the magnitude part, Gm upon Rd dash, and substitute this omega 0 back in this. I get a term Gm Rd dash upon 29. Substitute omega 0 here and get transfer function value at omega 0. Magnitude is Gm Rd dash by minus 29. Substitute here omega 0. Actually omega 0 by Rc 6 will come from here, so you will get 29. Now this, so what is the condition of oscillations to start? That gain should be larger than Gm Rd dash is actually a physical gain of an amplifier, okay. So that should be larger than 29 or equal to 29, slightly above 29, so oscillation can start and be sustained. Is that okay? So how do I adjust my Gm? By choice of bias current, okay, the DC, or I can also, if I am on integrated circuit, I can also choose W by Ls. I can choose the size of the transistors. In this specific case, we say only bias current can. So adjust your DC network to get whatever GM you want. Loads also you can adjust because you know RD dash will decide the gain, okay, so you can adjust that value as long as this value meets 29. Choice of current, what do you do? You may be given RD dash, for example. From there you will calculate GM, and for that GM find what is the bias current and go back and bias it properly. Is that okay? The method of design opposite, given it has to oscillate, this must meet this, go back and find GM and therefore I. That, and then given that RC you choose, this will be your oscillating frequency. Is that okay? So this is the basic phase shift oscillator, which is normally only used in discretes. Why did I say not used so much in the integrated circuits? Because I once said realizing a R on a silicon is large area problem, okay, so no one wants to use RC networks as far as possible, okay. I don't say never use it, as far as possible. So these are the issues which you all should know what we are talking about. There are other oscillators of interest, we will quickly go through some of them. A very famous oscillator credited to Mr. Wien, which is a Wien bridge oscillator. It consists of an op-amp, and what is this part is called R1 R2 part. Which feedback is this? Negative feedback. So please remember one important factor which I have not stated very obviously to you. There are both possible feedbacks are available, negative as well as positive. and the balance of the two will decide whether it will grow or it will damp. If it is stronger negative feedback, what will happen? It will damp out or fix a value. Okay. If it is otherwise, it may grow. And if we have both of them together, we may adjust when to oscillate. Okay. That's exactly what being tried here. Okay. I have a R1, R2 as the open loop gain is 1 upon, since it is a non-inverting amplifier kinds. So AOL is 1 upon R2 by R1, and the return voltage is something here, okay, which is returned to V plus. So how do you calculate? Let's say there is two impedances shown here. One is called series impedance, R and C in series. The other is parallel impedance, which is R parallel C. Okay, straightforward. This is in series, this is in parallel. So Zp upon Zp plus Zs is essentially Vp by V0, which is your feedback factor. Is that okay? This voltage by this voltage is essentially the ratio of this upon this plus this. So how much is Zp? Parallel combination of the R and C. So R upon 1 plus RCS. This is series, so Zs is 1 plus RCS by SC. Is that okay? I can substitute this in the beta factor. Is that okay? What I am going to do? What is the condition I am looking for? That the imaginary value be 0 and the real value be 1 to get a Barkhausen criteria satisfied. So I now substitute this here, get AO beta. What is AO beta? The loop gain. And in the loop gain, I will find real value, magnitude be real 1 at that frequency, and phase imaginary quantity be 0. Same procedure is always followed. So I substituted this Zp upon Zp plus Zs into 1 plus R2 by R1. ये मैं क्योंकि मैं कहीं से देख के लिखता नहीं हूँ, इसलिए मैं I write so many steps. You can write final step. Please remember, I write because I actually keep solving on the paper. I don't actually copy them anywhere. So I just have to do steps, because otherwise I cannot get this expression. Okay. So when I substituted all of this correctly, RCS to RCS, I get a term, and if I divide by RCS, I get, of course, sorry, that function is 1 upon 3 RCS plus 1 upon RCS. Very straightforward function is obtained. Then what do? Calculate Tj omega and then make imaginary quantity 0, and the magnitude at that frequency where this is 0, I get the Tj omega 0 is unity and fall for both of them. That's what I did. Okay. There is nothing really great I did. All that I substituted and got the value. For Barkhausen criteria, Tj omega should be 1 and hence real, and the imaginary be 0. So j omega 0 Rc upon plus 1 upon j omega 0 Rc is equal to 0, or omega 0 square R square C square is equal to 1. So omega 0 is 1 upon Rc, or the frequency of oscillation is 1 upon 2 pi Rc. Is that okay? So adjusting R and C, I can adjust the frequency. Is that okay? In integrated circuit, how could I have realized R? By what method? I just did last time. There is a filter I created using, anytime I want a pole, it's 1 upon RC. But in op amps, how do I get that? By getting GM. 1 upon R is GM, and GM can be attained by what way? Operational transconductance amplifier, OTAs. OTAs give you constant GM for proportion to currents. Okay. So this is again same GM upon C. So it's like same thing which we did. If I am realizing on a chip, I will prefer to use a OTA there to create GM values. Okay. So if I substitute this omega 0 is RC in this function, I get 1 plus R2 by R1 1 upon 3 is equal to 1, which gives me a condition that R2 by R1 should be equal to 1. To start, it should be slightly more than 1, because initially noise or some extra value has to be provided. So choose value of R2 by R1, that is, what is the gain I am talking? 3, that is the non-inverting gain is AOL is 3. If I adjust that, I will get oscillations at what frequency? 1 upon 2 pi RC. So it's a procedure is identical. Look for circuit, find its Tj omega by AOL and beta. That's why we did enough work on feedbacks. Why I spent so much time? Because that's the way all circuits can be easily implemented. I also, yes, phase is 180 degree. See, what I say at what is Barkhausen's two criteria I showed. One is it should be -1 as a value, which means magnitude 1 and phase 180. Is that clear to you? If you look at back your initial Barkhausen criteria, we said the magnitude be 1 and phase be 180 because Tj omega -1 we wanted. But alternatively I suggest if the real value exists at that frequency, the imaginary should be 0. That will give the same value. So at that frequency, yes, the impedance is real value. That's exactly oscillations are all imaginary quantities do not relate to any oscillations. This is the only procedure I showed you, either this or that Barkhausen criteria. Okay, it satisfies. I am using the second criteria most of the time. Okay, so हाँ ये जो एक्सप्रेशन है इसमें जे ओमेगा लिखो फिर आपको वो जो मैंने एक्सप्रेशन निकाला वो सही है. Okay, so we have now Wien bridge oscillator, we have then phase shift oscillators. Another oscillator, yes. Yeah, this is all sinusoidal oscillators. Yeah, but just think of it. The oscillators which we are right now talking are all sinusoidal oscillators. Okay. Yeah, that's you are perfect. You are actually employ this circuit and give a small noise signal of any frequency. Okay, and then you verify that fundamental frequency will come as 1 upon RC. Is that correct? What I have said. So it's not that I am talking because I wish to talk. These are sinusoidal oscillators and they will give me sinusoids. Okay. Any noise which is random, which may have one fundamental out of that, it will actually lead to that value. Okay. Is that point clear? You want to see non-sinusoidal? Yes, they will be coming soon. Okay. You are interested in those? Yes, we will be interested in. Where do we get interested in? Because on digital hardware I am looking for square waves. Okay, so yes, I will like to see what is the sinusoidal to non-sinusoidal conversions. Okay, very good. Another factor which is of interest other than the RC oscillator. What is the problem with RC oscillator? I say if I want to increase very high frequencies, what should be constraint on R and C? They should be very small. Higher the frequency, if you are used in your discrete discrete oscillator or discrete functions in the lab, to get a very low value of R, have you any time seen its tolerance? You see, go and look for say less than a ohm resistor. Probably our lab doesn't have metal film resistor which are less than a ohms. Now these tolerances are not less than 10. Okay, so get a smaller value of R with a reasonable value of tolerance less than 1% is very difficult, very difficult. And therefore one will not like to use normal RC oscillators for higher frequencies. Is that clear to you? It's not that I cannot, I can certainly reduce R and get higher frequencies. But one of the biggest thing what RC oscillators were giving me, I have a range of R and C products. Okay, and I can have number of frequency range I can attain. For example, just to give that idea, C can be a variable. How can make C variables? Variable capacitor. How do I get it? क्या होता है? एक ऐसा C वर्सेस V निकाला, ये किसका कैरेक्टरिस्टिक्स है? या इसका इक्विवेलेंट हम निकालते हैं 1 upon C square V. डायोड. So एक डायोड को यदि रिवर्स बायस किया तो it acts like a variable capacitor. So if I have a R and variable capacitor there, only guarantee you must say that at least you should have small capacitance already existing and add to this variable capacitor. इसका थोड़ा सा सोचो मैं क्या बोला. No explanation given to you. At no time circuit or same way R should have always be broken into two parts. Okay, let's say it doesn't short any time any circuit. Okay, so हमेशा जब सर्किट बनाते हैं प्रोटेक्शन क्या है, दो पार्ट्स में रखते हैं, एक तो भी चालू रहे, यानी जीरो नहीं कहीं पर, इन्फिनिट करंट नहीं होना चाहिए. Is that clear to you? So there are catches in lab which probably you don't use because you realize that गया तो किसी और का जा रहा है, घर पे यूज करेंगे और यार गया क्या. So that's the way life is. But anyway, so I can use varieties of vectors and can get a range of RCs. What will be these oscillators called? If I have C variable with voltage and frequency will be decided by 1 upon RC, C variable V. क्या oscillators का नाम होगा इसको? किससे कंट्रोल हो रहा है? Voltage. These are called voltage controlled oscillators, VCOs. Okay, so these are essentially, we'll come back to VCO better. That's what I'm trying to say. So we are always thinking R and R and R, so why not look for else? Okay. So we say we can use inductor capacitor combination to realize an oscillator, and these are called LC oscillator. There are a few things which are relevant to them. Compared to RC oscillators, LC oscillators are higher Q. क्या मीनिंग है हायर Q का मतलब? Q क्या होता है? क्वालिटी फैक्टर. इन टर्म्स ऑफ मैथ्स क्या होगा? ओमेगा L by R. R is the series resistance of inductor. Is that correct? This is something we are saying. Okay, before we go ahead, let me show you what I am really talking about. This is essentially called a tank circuit or a resonance circuit. Inductance parallel to a capacitor acts like a resonator or tank circuit. How does it work? If inductance is ideal and capacitor is ideal, initially let's say it has some noise or something, picks up something charge on this, that half CV square will be the energy stored. If I apply some voltage across this, half CV square energy will be stored on the capacitor. I remove the voltage, then it will discharge it through inductor and it will receive half Li square energy here. And since it is no dissipation going on, this energy will be dissipated back into capacitor and keep doing this infinite times. Okay, this is therefore called resonator. Okay, resonates at, and the frequency, if I equate impedance for this, then I will get 1 upon LC, root LC is the frequency at which this will resonate. Now in real life there is nothing called ideal inductance. So if there is a small r situated in series to an inductor, then IR will be a some drop, potential drop across, which means there will be loss of energy dissipated in the resistor. So what will happen? Every time you charge it back, some energy will be lost, so as if oscillation will start damping down. Okay, so this is essentially, we say energy dissipation factor is called the quality factor. And therefore if R is 0, which is ideal, how much is the Q for this? Infinite. So larger the Q, better is the tank circuit. That means the frequency response will be something like this, sharper response at a given frequency. Is that correct? Ideally where it should be? Go to infinite. Okay, at that frequency only it should have value, other places no value. But that may not occur in real life. It may have some narrow band in which it will rise and fall. Okay, and the maximum will occur at resonating frequency. So is that point clear to you? So a LC tank circuit or LC resonator circuit is the best way to create oscillations. The only problem, as I said, that since it's going to lose some energy, it must be replenished. All that we are saying is replenishment of lost energy, and if that happens, oscillation will be sustained. Is that clear? Oscillations will be sustained. जितना energy उतना दो ना, तो permanently LC पर oscillate करता है. Is that clear to you? This is the trick which we follow in all LC oscillators. So that is what I was saying to you. It has a very high Q, 1 upon omega RC omega L by R, and therefore since inductance value vary from very small to very high, inductance can be as low as femtohenries or at least nanohenries or below picohenries. अच्छा, यदि रेजिस्टेंस कम करना है तो इंडक्टेंस का क्या करने से रेजिस्टेंस कम हो जाएगा? What should be the type of inductance I should use? Type means inductance is generally wire bound. Okay. So wire का क्या property है जो resistance कम करेगा? Thicker wire, is that correct? So if you are using a thicker wire, area is higher, obviously its resistance is lower. Okay. So if you have seen a transformer, you see how thick wires they actually wound. Okay, because of very low inductances they wound there. Okay. Okay. So because inductance values can be minimized and capacitance for a diode or any other can be reduced, at least go to femtofarad. We have seen in MOS transistors how much capacitance I could go down, up to femtofarads. So I have very large frequency operation possible with LC oscillators. So is that clear? Why not RC? People always ask this question, that when RC was doing so great a job, so simple a job, why are we looking for an LC network at all? The reason is obviously at much higher frequency of operation, the problem is low dissipations and very high frequency operation. The only difficulty it will give is at one frequency it will operate, tank circuit, which what it means is bandwidth relatively where up to which it can give frequency will be limited. In RC, you have a wide range of frequencies attainable. Is that clear? That is the advantage which RCs provide over LCs. Therefore, we say tunability is very small, but doesn't matter. It gives a very high frequency performance. Where do you think we need high frequencies? Mobiles. We are working on, say, whatever 2G or 3G or whatever 890 megahertz and above. If you are working on Bluetooths, you are working on 2 to 4 gigahertz E-bands. So if you are working on higher, people are now looking for 60 gigahertz satellite phones. Okay. So we are really looking for very high frequency generations. These are not the only generating systems. There are different other generators. RF course should teach you what are those. Okay. But right now we should say any LC oscillator is therefore used only for constant frequencies, very sharp frequencies and much higher frequencies. Okay. There are two very famous LC oscillators in literature. They were first made, if you are, I don't know whether you recollect, very first talk I showed you some diodes made out of vacuum tubes, Lady Forest vacuum diode, huge 6-inch tube. First oscillator was made using vacuum tubes. Okay. So it's not that it's present, but let's see which are these two, Colpitt's oscillator and Hartley oscillator, very famous oscillators. Last 70-80 years these are popular. The other oscillator which is the most important oscillator in every work where we are working right now is a crystal oscillator. So is that clear? Why I am clubbing this with LC? Obviously I believe that the crystal equivalence is like a LC network. This is my assumption which I can prove but not in this course. Okay, so let us say typical BJT based oscillator, and then I will show you a equivalent of MOS equivalently. I will just show you the circuit diagram. What is Colpitt is saying? Okay, you have a transistor, how much phase it will give me? 180 degree. This is my load across. This is the AC equivalent. Huh? Please remember this R is essentially the load. Is that clear to you? R is essentially the load. Then I put a tank circuit across this. But I did mischief there. I divided this net capacitance into two parts. The center one I grounded and I put this C2. So what is the purpose of this grounding in between, and what is essentially it is trying to give you? What is this voltage across this is going where? ये वोल्टेज है जो आउटपुट पर है, ये कितना है? इसका रेशियो के साथ यहाँ पर आ रही है, कहाँ जा रहा है? फीडबैक हो रहा है. So this C2 is essentially creating a feedback for you. Is that okay? This is the net output voltage divided by, this is a divider, this is a ground potential, C2 upon this plus this is essentially giving me the feedback factor. Okay. So I am now looking into a transistor plus LC network with a load here with a divider to make this. I can do just the opposite of Colpit. What is opposite means? जहाँ C है वहाँ मैं इंडक्टर रखूँगा, जहाँ इंडक्टर था वहाँ मैं कैपेसिटर रख दिया. Same circuit, replace L by C. This circuit is called Hartley oscillator. It's like a derived situation. इस आदमी ने पहले बनाया, इस आदमी ने सोचा कि समझो उल्टा किया तो क्या आता है. ये डिराइव्ड सिचुएशन. इसका ऐसा था, इसको उल्टा करके देख लेता हूँ. तुमको एक प्रॉब्लम दे दिया, तुमने करके दे दिया, हमने छाप भी दिया. That is what all research is about, but that's what your thinking is. Okay, if this works, the other should, corollary must work for it. Corresponding system must work for you. So, a duality hai that here. Have you heard any time this word duality in your physics course? So, whole nature is in duality right now. Matter or waves, यहाँ भी वो problem. Duality is a game in the life. Okay, एक डिराइव करके दिखा देते हैं. उसी सर्किट को थोड़ा सा ऐसा करके रखा है. डोंट फील वेरी सैड अबाउट कि वो वैसा नहीं दिख रहा है, वही सर्किट है. ऐसा क्यों लिखा? क्योंकि सेड्रासिस में ऐसा फिगर था, तो मैं बोला फिर आप फिर से ऐसा क्यों करो. वो वही है, वो इधर फीडबैक पर है, ये रेशियो है, ये V0 है. ओके, देयर इज नो डिफरेंस. दिस टर्मिनल इज सेम एज दिस टर्मिनल. तो यही V0 है, ये V0 है, ये V0 है, ये V0 है. ओके, इसका इक्विवेलेंट किया. This is my VGS across C2. Okay, or rather, okay, ये उल्टे लिखे गए हैं, ये C2 C1 है, doesn't matter. Then इसका इक्विवेलेंट बनाया, which is trivial. Okay, आप इक्विवेलेंट सर्किट बनाने के बाद क्या कर सकते हैं? दो लूप्स की, कहाँ लूप दिख रहे हैं आपको, या नोड वोल्टेज V0 पर क्या दिख रहा है आपको? एक ये है और एक ये है. प्लीज लुक एट इट. आई एम नाउ सीइंग करंट्स एट दिस नोड V0. का क्या क्या करंट है? V0 by R, एक ये करंट है, एक GM VGS करंट है, सेम डायरेक्शन में. ओके, V0 upon 1 upon SC1 इज अनदर थर्ड करंट. और फोर्थ करंट किधर है? जो इंडक्टर के तरफ से जा रहा है. इज दैट क्लियर? ये आपका VGS है. If you say this, then it is V0 upon Ls plus 1 upon SC2 is the fourth current. All currents should sum up to 0 by Kirchhoff's law. So this is equation 1. If I want to calculate VGS, कितना होगा? This upon Ls plus 1 upon Lc. इसका जो टोटल है, थोड़ा सा वैल्यूज, अब ये C1 C2 मेरे गलत हो गए, आप जरा देख लो. आई थिंक आई मस्ट बी राइट, दिस शुड बी C2, करेक्ट. सो 1 अपॉन SC2 अपॉन Ls प्लस इंटू V0, इसको एक्सपैंड किया, दो इक्वेशंस आ गए. इसमें VGS की वैल्यू यहाँ सब्सटीट्यूट करिए, सॉल्व करिए. इज दैट ओके? सब्सटीट्यूट दिस VGS in the equation 1 and then all terms will be in what? V0 terms. All terms will be V0 terms. Okay, if V0, I just collected the term GM plus SC2 plus 1 plus LC2 S square into 1 upon, yes? Yeah, of course you write down, I have no objection, but I just want to say you these are now quite trivial. They are quite trivial because we are just solving Kirchhoff's law and nothing great. You can ask sir why आप इतना टाइम वेस्ट करते हैं? क्योंकि मेरे पास एक्सप्रेशन पहले रहता नहीं है, इसलिए I had to solve to get that expression. Okay, that's the way I am. So if you collect, of course this is given in Cedra Smith's book, so it's nothing really great. I just checked latter कि क्या क्या देते हैं वो. Now if oscillation is to sustain or start, V0 क्या होगा? 0 होगा क्या? Yes, if V0 is 0, there are no oscillations. Is that output 0 है ना? No oscillation. So if V0 has to be finite, then, and if this equation has to be correct, then the term inside the bracket must be 0. Okay. If I substitute again, substitute S is equal to j omega, real value plus imaginary value 0 है. बारखाउजन क्राइटेरिया कहता है कि at omega 0 पर real value should be 1 and imaginary value be equal to 0. Okay. सॉल्व किया, इस टर्म को 0 किया, so I got omega 0 square LC2 upon R is equal to, sorry 1 कर किया तो GM plus R this, or this will give me omega 0, इसको सॉल्व किया, सॉरी ये इसकी वैल्यू अभी नहीं निकाली, हाँ ये रियल वैल्यू यदि 1 है तो GM plus 1 upon R is omega 0 square LC2 by R, और टू से ओमेगा 0, ये इंपॉर्टेंट है, अभी ओमेगा 0 की वैल्यू आनी है, विल सब्स्टिट्यूट हियर, दिस इज इक्वल टू 1, ओके, रियल वैल्यू शुड बी इक्वल टू 1, दिस इज माय रियल वैल्यू, ओके, सो इसको 1 किया है तो ये एक्सप्रेशन आ गया मेरे पास. ओके, हाउ टू गेट फ्रीक्वेंसी ओमेगा 0? बाय इक्वेटिंग इमेजिनरी क्वांटिटी टू, I just made this 0 and this 1 for Barkhausen criteria at omega 0. Okay, at oscillating frequency the real part should be 1 and imaginary part be 0. Okay, sustained oscillation करना, तो इसको 1 किया तो ये टर्म आ गई, इमेजिनरी को 0 किया तो ओमेगा 0 मिल गया मेरे को, 1 upon root L C1 C2 upon C1 plus C2. इस ओमेगा 0 को वो लास्ट फंक्शन में सब्स्टिट्यूट किया, सो आई गॉट ए रेशियो ऑफ C2 by C1 is equal to GMR. As long as your GMR has a value of C2 by C1, okay, slightly greater than C2 by C1, that oscillator, Colpit oscillator will oscillate at 1 upon root L C1 C2 upon C1 plus C2. R क्या है? लोड. GM कहाँ से आने वाला है? बायस से, जो बायस करंट लगाएंगे उससे GM मिलेगा. C2 by C1 you are going to adjust, you are going to get a frequency from here, a value of C2 by C1, assume one capacitor and get the second one, substitute here and you will get frequency of oscillation. Vice versa क्या है? Given a operating frequency, get the ratio of C1 C2 from here, come back, substitute here and say okay, what should be GM to sustain this frequency. Is that clear? This is design. Why it is called design? Because I am not interested in GM value or R value, I am interested should oscillate at 100 megahertz or 800 megahertz, that's what I will say. So what do I give? I go this expression, evaluate C1 by C2, come here and find what GMR I should use to have a oscillations. GM I will adjust by bias. Is that okay? Is the design clear to you? I am always telling you what's the design. Design is just the opposite in that sense. Output will be told to you, this is what I want. Come back and find what should lead to this. Okay, this is how we do it in designs. Okay. तो आपको यहाँ से ये दिया होगा तो इसका, अच्छा उसमें भी फिर है, inductance will have to assume or I will be giving you. Typically inductances per higher frequency should be less than 1 nanohenry. Less than, एक typical value बता, why it should be less than 1 nanohenry? Can you think of it? आप यदि गीगाहर्ट्ज में जाना चाहते हैं तो यदि नैनो से कम नहीं रखेंगे और सी भी पिको में रहेगा तभी आप नैनो गीगा में जा सकते हैं. गीगा इज 10⁹, स्क्वायर मीन्स 10⁻18 वैल्यू लानी है आपको स्क्वायर टर्म में करने के लिए. तो यदि इनके दोनों का प्रोडक्ट 99 नहीं होगा, -9 से नीचे नहीं होगा तो ये 18 नहीं ला पाएंगे आप ना स्क्वायर में. तो इसलिए हमेशा ध्यान रखें कि इंडक्टेंस शुड बी लेस देन ए नैनो हेनरी. typically 0.0, 0.8 or 0.6 nanohenries are used. Even lower can be used for higher frequencies. Is that correct? So length, typically inductances are decided in chip by the wire. Which wire? The bonding wire बोलते हैं chip का सिलिकॉन से जो नीचे पिन आती है उसमें एक अंदर एक वायर बाउंड करते हैं वायर, वो वायर का इंडक्टेंस ही लेस देन नैनो हेनरी रहता है, वो यूज कर लें. वी डोंट इवन पुट एन इंडक्टेंस. ओके, दिस इज व्हाट द गेम इज ऑल अबाउट. तुमको थोड़ा डिजाइन इशू बता दिया क्या करते हैं. हार्टले करना है तो क्या आना चाहिए, क्या होना चाहिए, थोड़ा सा वैसा ही फिर से सर्किट सॉल्व करिए और हार्टले ऑसिलेटर की कंडीशन आएगी 1/L1 plus L2C under root of that will be the Hartley frequency. Is that point clear to you? कोलपिट और हार्टले में कोई फर्क नहीं है, उसमें रेशियोज C के हैं, इसमें रेशियोज इंडक्टेंस के हैं. ओके, थोड़ा सा फंक्शन सिंप्लीफाई हो जाएगा इंडक्टेंस में. क्यों? क्योंकि वो 1/j ऊपर ही रहता है, इसमें 1/CS नीचे आने से हमेशा वो दो टर्म लेके आते हैं. ओके, इसमें थोड़ा सा रिलेटिवली इजियर एक्सप्रेशंस आते हैं. Okay, so we have already said that two popular LC oscillators are discussed, one using Hartley technique, one using Colpitt's method, the other is using this. इसके पहले कौन से oscillator यूज किए? Phase shift oscillator, which are essentially RC oscillators. Okay. अब एक नया oscillator जो आप we all use and I think all of you have used. The last oscillator which we use very often from this kind LC oscillators is called crystal oscillator. Normally crystals which we use are quartz crystals. आपको समझो बोला 33 किलोहर्ट्ज का क्रिस्टल चाहिए या 3 मेगाहर्ट्ज का 3.1 मेगाहर्ट्ज का क्रिस्टल चाहिए, तो क्या देख के बता सकते हैं कि ये 3.1 मेगाहर्ट्ज का है और ये 33 किलोहर्ट्ज का है? क्या दे? क्रिस्टल तो ऐसा पीस मिलता है आपको, हाँ सील रहता है, उसके लीड्स 2 लीड्स निकले रहते हैं. क्या बता सकते हैं कि ये लोअर फ्रीक्वेंसी का है और ये हायर फ्रीक्वेंसी? नीचे लिखा है मैंने, थोड़ा पढ़ो. द फ्रीक्वेंसी डिपेंड ऑन द मास ऑफ द क्रिस्टल और द साइज ऑफ द क्रिस्टल. लार्जर मास होगा तो क्या होगा? हायर फ्रीक्वेंसी होगी, कम फ्रीक्वेंसी होगी. सो जितना बड़ा क्वार्ट्ज क्रिस्टल खरीदेंगे उतनी लोअर फ्रीक्वेंसी का रहता है, जितना छोटा क्वार्ट्ज क्रिस्टल खरीदेंगे उतना वो हायर फ्रीक्वेंसी के लिए रहता है. What is the property of crystal? It follows a electromechanical resonance. उसका दूसरा नाम क्या है? Piezo effect. It's a piezoelectric effect. If you apply a electric field to such materials, then it provides mechanical vibrations or vice versa. Okay, this is also doable. Okay. Piezoelectricity is the word which we use there. So what we do is that we pick up a quartz crystal with soldered contacts on that. Okay. And advantage of these crystal oscillators is it is temperature independent to great extent. It's not correct. All 2000 डिग्री पे वो भी ये हो जाएगा, 1450 डिग्री पे क्वार्ट्ज मेल्ट हो जाता है, 800 डिग्री से ही एक्चुअली फ्लो शुरू हो जाता है. इसको बोलते हैं ग्लास फ्लो. और या सीन इट ना, ग्लास ब्लोइंग करते हैं ना फ्लेम के ऊपर, तो 1400 तक तो पूरा मेल्ट होता है. तो ऐसा मतलब ये मत सोचो कि किसी भी टेम्परेचर, बट नॉर्मल ऑपरेटिंग रेंज इज 150 डिग्री टू -55 डिग्री सेंटीग्रेड. अलास्का से लेकर राजस्थान के डेजर्ट तक वो चलना चाहिए. ओके, सो दिस इज टेम्परेचर इंडिपेंडेंट. टाइम स्टेबल मीन्स क्या? आज एक फ्रीक्वेंसी, कल थोड़े दिन बाद दूसरी फ्रीक्वेंसी नहीं आनी चाहिए. So it is time stable. Okay. So that's why it is used extensively. But what is the difficulty with this? It is non-tunable in fact. It's a fixed frequency oscillator. इसका जो भी natural frequency है वही oscillate करेगा. Now funny part, the crystal oscillator which I am going to show you now does not really work the way we thought. Okay. Crystal oscillator is like a tank circuit. Okay. The only difference between this circuit and the equivalence is something different. It has an inductance, it has a series capacitance Cs, it has a small series resistance R, and it has a parallel capacitance LCSCP. This is equivalent circuit of a crystal. Okay, I'll come back to it, but just to show you. So this is the resistance. So Q कब ज़्यादा होगा? जब R जो है 0 के तरफ. टिपिकली क्रिस्टल्स के Q जो है वैल्यू है, एनीवे आई एम शोइंग यू दैट वैल्यू. टिपिकल Q जो है 10 to power 4 से ज़्यादा रहता है एक्चुअली. What does that mean? R is practically 0. Omega L by R is 10 to power 4, which means R is very small or negligible. So टैंक सर्किट का क्रिस्टल ऑसिलेटर में जो इक्विवेलेंट सर्किट यूज होता है वो ये होता है. LSCS, LS नहीं कहते क्योंकि वो सीरीज में, LCS shunted by CP is the equivalent circuit of a crystal. R is present, but as I said, normally Qs of all quartz crystals are more than 10 to power 4. So R is neglected in all analysis. Problem क्या है, R रखोगे तो सर्किट लेंथ बढ़ जाएगी, एक्यूरेसी कुछ बढ़ती नहीं. Okay. So if I say, before I come, the frequency depends on size. Most important quality of this quartz crystal is it has a very large Q, and Q is greater than 10 to power 4 or above. Okay. So equivalent circuit of a crystal, और मैं जो अभी तक बोला वो सब, अच्छा ये values लिख लो. Typical R is less than milliohms, so we just get it. The inductance of a quartz crystal equivalence is around 100 henries. The series capacitance is around 0.5 femtofarads, and the parallel capacitance is of the order of few picofarads. Is that okay? L, CS, R parallel CP is the equivalent circuit of a crystal. तो R को तो मैंने 0 कर दिया, ये इसकी टिपिकल वैल्यू है. और दिस इज द सिंबल ऑफ ए क्रिस्टल. कैन यू थिंक व्हाट इज द सीपी वैल्यू इज कमिंग फ्रॉम? ये फिगर से कुछ लगता है क्या तुमको, क्या होगा सीपी वैल्यू? पैरेलल प्लेट कैपेसिटर का जो कैपेसिटेंस है वो उसका सीपी है. इज दैट करेक्ट? तो बाहर के टर्मिनल पे जो भी दिख रहा है वो उसका सीपी है. व्हाट इज सीएस कुड बी? This is because of the what is called dipole moment of the ionized material kept there, which is in inductive series to that. So that is CS, which is typically less than femtofarads. Okay. If इसका यानी मैंने ZS निकाला, reactance Y निकाला समझो इसका, and if I plot it versus frequency, okay, Z है ना या Y है, इसका ओमेगा के टर्म में प्लॉट किया, so I figure out that at omega equal to omega s, which I call series frequency of this, okay, omega s, इसके नीचे फ्रीक्वेंसी पर यह कैपेसिटिव बिहेवियर करता है. Why it becomes capacitive in lower frequencies? 1/j माइनस साइन आया, इसलिए ऊपर गया तो प्लस साइन आया. और इसके आगे आइसिम्प्टोटिकली ओमेगा पी तक वो हायर वैल्यू लेता है इंडक्टेंस. इज दैट ओके टू यू? एंड यदि ओमेगा पी के इधर देखा तो सीपी इसको डोमिनेट करता है और उसका ये कैपेसिटिव रहता है. ये सी एस एल एस का कॉम्बिनेशन है और ये सीपी का है. ओमेगा एस इज द सीरीज फ्रीक्वेंसी, रेजोनेंट फ्रीक्वेंसी. ओमेगा इज पैरेलल रेजोनेंट फ्रीक्वेंसीज. Series and parallel resonant frequencies are called omega S, omega P. Please remember, tank circuit, even series LC circuit is also a tank circuit and it has own 1/LC as its frequency. Is that correct? It's called series frequency. Parallel करेंगे तो भी 1/√LC जो आ रहा है वो भी parallel combination पर है, उसको उसका parallel resonant. The reason why it is different will be obvious when I show you that. Okay. Now, as I say, CPs is very large compared to CS. What does that essentially means? If CPs are much, that means omega S, यदि terms इसकी निकाली तो omega S and omega P ये बिल्कुल ही एक दूसरे के पास रहते हैं. If they are very close to each other, what does that mean? That means anything less than this frequency, the crystal will act like what? capacitor. Anything slightly larger than omega s but limited by omega p, what will it act like? Inductor. So crystal oscillator वाले लोग कह रहे हैं कि आपने जो कोलपिट oscillator बनाया था, उसमें क्या बनाया था आपने? दो कैपेसिटर और एक इंडक्टर डाला था। तो इस इंडक्टर के जगह आप एक क्रिस्टल लगा दीजिए। And up to what frequency? At what frequency it will always give you inductive? Between omega s and omega p. That's why it's called tuned. इस नैरो बैंड में ही वो सिर्फ इंडक्टेंस बिहेवियर देगा और वो ऑसिलेट कर देगा कोलपिट के मेथड से। इसका जो इक्विवेलेंट इंडक्टेंस है, इसके जो फॉर्मूला मैंने कोलपिट का दिया है ना, वो वही है। इसमें इंडक्टेंस की वैल्यू विल कम फ्रॉम दी crystal. Is that okay? So this is how crystal oscillators are actually used. Crystal oscillators do not really give its own oscillation per se directly. They fit into a Colpit combination and you replace your inductance by a crystal. Okay, and the voltage here should be such that, and the frequency that we are operating should be such that this behaves like an inductor, that those frequency this Colpit oscillator will oscillate between omega s and omega p, and if C1 is much larger, whatever the value I give, larger or smaller, if Cp is much larger than Cs, then omega s and omega p is very close to each other, and which means at that frequency this will oscillate permanently. तो एक क्रिस्टल, अच्छा इसका एडवांटेज क्या है? द नैरो बैंड, दैट मीन्स शार्प है, it is stable because crystal and it is temperature independent. Is that correct? जो भी टेम्परेचर इंस्टेबिलिटी यहाँ से आने वाली वो किससे कम हो रही है? Why it will be much less? ये कौन सा फीडबैक जा रहा है? फीडबैक आया ना, उसको स्टेबलाइज कर देगा वो। ओके, इसके कारण हिलने नहीं देगा, ये इसको स्टेबलाइज कर देगा। तो दिस सिस्टम इज परफेक्टली यूजेबल in any system where you are looking for oscillations of constant frequency independent of time and temperature. Is that correct? This is called crystal oscillator. So there are some other version op-amp के साथ books में देखो. Okay. मैंने आपको basic बताया कि how do I use a crystal in any oscillating systems. Omega p is because of L and Cp. It has an equivalent. See the piezoelectric effect, if I apply voltage, the natural frequency is equivalent of putting this tank circuit. It's a piezoelectricity theory which I am not solving for you. Okay. You assume right now equivalent circuit is this. Okay. Omega s cannot be later because CS बहुत छोटा होगा तो हमेशा ये इधर ही रहे LC. क्योंकि equivalent circuit Z, idea is write ZS and find that. Okay. Is that okay? Which I haven't done it, but I just showed you what to do. ओ सॉरी, ये थोड़ा सा गलत हो गया है। ये जो है कहाँ होना चाहिए कोलपिट में? ये यहाँ वीओ एंड ड्रेन, हाँ ये भी वीओ ही है ना, सॉरी सॉरी सॉरी, ये भी वीओ है। ओके, essentially sorry, but essentially what I was saying that you just use a crystal in place of inductance, rest Colpit remains similar. सो एक आदमी मुझे कह रहे थे कि सब सिनुसाइड है, तो चलो एक और आपको पहला दिखाते हैं, नॉन सिनुसाइडल। ओके, बाकी उसके बाद थोड़े दिन नेक्स्ट टाइम बताएंगे। हियर इज अ सर्किट विच इज यूज्ड फॉर रिंग ऑसिलेटर। व्हाट इज रिंग मीन्स? इट्स ए रिंग। दीज आर स्टैंडर्ड इन्वर्टर्स। ओके, 1 2 3 और मैंने लिखा है ऑड नंबर। नाउ एक थोड़ी सी थ्योरी करके देखें, ये ड्रॉ कर लो आप। ये सॉरी नॉन इन्वर्टिंग इन्वर्टर नहीं है, सॉरी, दे आर ऑल इन्वर्टिंग इन्वर्टर्स। द वर्ड आई हैव यूज्ड, हैव यू हर्ड ऑफ दिस वर्ड? नॉन इन्वर्टिंग इन्वर्टर्स, buffers. The idea is simple. I have an inverter Let's say the capacitance here and a load capacitance here. This was storing 0, so this will store 1, okay. But next time ये 1 इसको चार्ज करेगा तो ये फिर ये 0 ये 1 होता है, ये depending on the delay it will keep changing. So at any given time I don't know whether output is 1 or 0. Phase कितना है, 180 है इसमें सिर्फ. So this cannot oscillate, it can't sustain a frequency. तो मैंने कहा अच्छा ये बात है क्या, दो इन्वर्टर लगाए, एक का 180 दूसरे का 180, 0 1 0 इन फेज रिटर्न हो गए, तो ये तो ऑसिलेट करना चाहिए था, नहीं करता है. क्यों नहीं करता है, फिर से बताए. 0 180 180 180 360 पे इन फेज आ गया, क्राइटेरिया सॉल्व हो. तो अब देखो इसमें कहीं तो भी बार्कहाउज़न क्राइटेरिया सॉल्व नहीं हो रहा, मीट नहीं हुआ. ये जहां भी मीट कर रहा है, मैं आपको इसकी थ्योरी नहीं बताऊंगा, आप सोचो नहीं तो नेक्स्ट of operation, the omega 0 where it can become unity is only 0. What does 0 means? DC. So this will oscillate for DC. Yes. यदि 1 यहाँ 5 वोल्ट है तो यहाँ 0 वोल्ट है तो यहाँ 5 वोल्ट है, ये करता है, DC वैल्यू फिक्स रहेगा. So it is a DC oscillator which is not oscillator. इसको क्या बोलते हैं एक्चुअली ये सर्किट को? अब इसका सर्किट का दूसरा फिगर बताता हूँ. क्या है ये? लैच. ये लैच है तो फिक्स कर देता है, लैच कर देता है वो. ओके, सो इट्स स्टिल एन ऑसिलेटर फॉर अ डीसी, बट डीसी ऑसिलेटर इज नॉट कॉल्ड ऑसिलेटर. सो एसेंशियली two inverters, though it gives phase value correctly, it does satisfy Barkhausen only at 0 frequency. Therefore it doesn't really oscillate. इसलिए क्या जरूरी हो गया अभी कि 2 से तो ज्यादा इन्वर्टर लगानी पड़ेगी. Is that clear to you? Why more than 2? Otherwise it will never oscillate. ये तो 360 मिला आपको, फेस तो एडजस्ट कर दिया मैंने, पर मैग्नीट्यूड 1 नहीं करेगा इस फ्रीक्वेंसी. जहां वो 1 कर रहा है ट्रांसफर फंक्शन, वो सिर्फ 0 डिग्री 0 फ्रीक्वेंसी भी कर मैच हो रहा है. आप करके देखो ना, ये इसीलिए मैं बता नहीं रहा, आपको बता दिया कि इसका इक्वलेंस ये है, बाइस्टेबल एलिमेंट है. यही मैं आपको बताना चाहूँ कि थोड़ा कैसे सोचते हैं लोग, मैंने आपको थोड़ा हिंट दिया. वेरी रिलेवेंट, व्हाई 2 इन्वर्टर्स डू नॉट एक्चुअली ऑसिलेट. ओके, सो यदि ऑड इन्वर्टर्स लगाए और हर एक में एक कैपेसिटर भी लगाया, 3 लगाए समझो, तो दिस इज, इसके अंदर एक रेजिस्टर्स होंगे इक्वलेंटली, ऑन रेजिस्टर ऑफ रेजिस्टेंस जो होंगे. तो ये जो आरसी नेटवर्क है ये 180 180 180 यानी एक्चुअली 180 हुआ, प्लस नेटवर्क से 180 लाया, तो टोटल फेज 360 पे आएगा. और यदि ये समझो 5 हैं, समझ लीजिए एक और बीच में डाल दिया, तो एनी ऑड नंबर will actually give you 180 and network will give you another 180 like a phase shift oscillator. So it will start giving you square wave generation. पर यदि आपने एक लैब में एक्सपेरिमेंट कभी डिजिटल में किया होगा तो हम एक्चुअली क्वाड एरे लेते हैं, 4 इन्वर्टर का एरे लेते हैं और उससे रिंग ऑसिलेटर बनाते हैं. क्यों बनाते हैं? थोड़ा सा आपको अलग अलग हिंट्स दे देते हैं. ऑसिलेटर तो यही है, हाँ, पर यहाँ एक ये क्या काम करता है, ये जो V0 यहाँ है इसको क्या करता है, ये बफर कर रहा है. क्यों करना चाहिए बफर? व्हेन यू स्टार्ट मॉनिटरिंग ऑसिलेशंस हियर, क्या लगाएंगे आप स्कोप पे देखने के लिए, क्या लगाएंगे यहाँ पर, वो प्रोब लगाएंगे वहां पर. उसका कैपेसिटेंस इतना ज्यादा है कि ये जो आपके नेटवर्क में सी डाल रहे थे वो सेम नहीं रहेगा, तो वो ऑसिलेट नहीं कर पाएगा. आप जैसे ही प्रोब को वहां पर लगाएंगे, the last capacitor will change, the phase will not remain 180. Is that clear to you? So the buffer essentially takes you out of that probe business. Is that correct? So in real life में एक चौथा इन्वर्टर लगता है जिसके आउटपुट पे हम एक्चुअली इन्वर्टेड आउटपुट देखते हैं. Is that clear to you? Okay. So let's so we want to see some kind of a square wave generation or even triangle or any sawtooth. कैसे बनाएंगे? तो इसके लिए एक सर्किट है, बस इंट्रोड्यूस करता हूं मैं और फिर नेक्स्ट टाइम आता हूं। एक और सर्किट हमें यूज करना पड़ेगा, वो सब करने के लिए उसका नाम है कंपैरेटर। उसका नाम है कंपैरेटर। यस, जितने कैपेसिटर आरसी टोटल मिलके 180 डिग्री क्रिएट करना चाहिए। और इन्वर्टर्स का फेज 180 आएगा, 360 प्लस 360 या 720 प्लस एक 180 आएगा। नेटवर्क से 180 आना चाहिए, तो फेज रिटर्न होते समय 360 रिटर्न होना चाहिए। फेज शिफ्ट ऑसिलेटर का जो प्रिंसिपल है वो यूज किया है। इज दैट करेक्ट? इन फेज कंपोनेंट वापस रिटर्न होना चाहिए। इज दैट करेक्ट? ऑल द नहीं, वो तो सॉल्व करना ही पड़ेगा ना। ट्रांसफर फंक्शन वैल्यू इमेजिनरी 0 और रियल वैल्यू 1 करके करना, हम करके नहीं दिखाया, हमने आपको बताया कि ऑड से ही हो सकेगा, अदरवाइज नहीं। ओके, यू आर राइट। एक ओपैम है, उसको यदि ओपन डिफैम जैसा यूज किया, नो फीडबैक, you have two inputs V1 and V2, your power supplies are VDD and VSS, let's say 5 and minus 5, 2.5 minus 2, whatever values you put, and you have a V0. ये सादा डिफैम का आउटपुट है। इसका क्या होगा? V0 A टाइम्स डिफरेंस ऑफ दिस, बट इसका गेन क्या होता है? माइनस A टाइम्स V1 माइनस V2 को क्या बोलते हैं हम लोग? डिफरेंस वोल्टेज। तो A times Vd with a minus sign is the V0. Is that clear? Vd is the difference signal, V1 minus V2. A times, this is डिफैम का थ्योरी है, डिफरेंस गेन के टाइम सिग्नल एम्पलीफाई होता है। If I plot this same thing on a sheet, on a graph, V0 versus differential, I see some small less value of, say this is V1 minus V2, at 0, if there is no offset, output is 0. Okay. If V1 minus V2 is positive, or rather it should be opposite sign because it's a minus sign, ठीक है, इसको minus ले लेते हैं अभी। It should, rather than as simple as that. Okay. If it is minus, the output will go high, and if it is plus, output will go minus VSS. इस वैल्यूज को मैंने नाम दिया है VH एंड VL. What is the gain function? dV0 by dVin is the gain of any amplifier, which is in this case VH minus VL by point, this, the x value delta delta equal है वो दोनों. So if I substitute this 5 volt 5 volt, and let us say the gain is 10 to power 5 for open loop gain for this op-amp I use or diffam, then 2 delta is 0.1 millivolt. Is that clear? 0.1 millivolt. और गेन बढ़ाएंगे तो और भी 100 माइक्रोवोल्ट से भी नीचे आ सकता है। okay. तो यदि मैं समझ लिया कि गेन बहुत ज्यादा है, so this characteristics can then look, delta will become close to 0. If this value is very high, then tends to infinity, let's say, delta will tends to 0. So what will ideal op-amp का गेन यदि infinite माना, तो ट्रांसफर कैसा होगा? at V2 minus V1, okay, Vd पॉजिटिव है, तो ये Vd पॉजिटिव है तो माइनस VSS पे चला गया, Vd निगेटिव है तो प्लस VDD पे चला गया। इज दैट करेक्ट? ये क्या दिख रहा है आपको? ये कैसा कैरेक्टर्स दिख रहा है? इसको मैकेनिकली या इलेक्ट्रिकली हम क्या बोलते हैं डिजिटल में? स्विच. सो ए कंपैरेटर विथ ए हाई गेन creates like a switch. स्क्वायर वेव क्या होती है? ऑन ऑफ ही है ना, ऑन ऑफ. ओके, so now you can think that if I have a comparator, I should be able to create on off situations, which means square wave. Is that point clear? नेक्स्ट टाइम यदि यहाँ किया तो मैं एक स्क्वायर वेव को कंपैरेटर के तरफ से क्रिएट कर सकता हूँ. सो एक कंपैरेटर other than comparison itself is another advantage it has. It will also give me equivalent of a on off switch, okay, and that I can utilize to create square. ट्रायंगल करना है तो क्या करना चाहिए? स्क्वायर का ट्रायंगल कैसे करते हैं? ऊपर गया ऐसा करना, इंटीग्रेट करो, बस एक इंटीग्रेटर लगा दो तो स्क्वायर का इंटीग्रेट होके ट्रायंगल हो जाएगा, ठीक है। उसके वोल्टेज कम ज्यादा करना है, क्या करना चाहिए? एक लिमिटर डायोड क्लैंपिंग करो, जिस वोल्ट पे चाहिए वहां रोक लो उसको, है ना। सब कुछ जो अभी तक पढ़ा है वो लगाया जा सकता है। इज दैट करेक्ट? दिस इज एसेंशियली व्हाट द नॉन sinusoidal oscillators do using comparators. But pure comparator हम use नहीं करेंगे. The kind of comparator I am going to use is called Schmidt trigger. So next time we start with Schmidt trigger.